Yes, class. Am I audible?
Yes, ma'am.
Anushka, Imad, Rayan, Razan, and Astha. Okay, so we had started with a comparison of electrostatics and magnetostatics and the formula of magnetics. We had seen. We didn't do any numericals, no? Let's use some numericals. You have to find the magnetic field at this point P. See this. Yes, Anushka.
Ma'am, what about the marks of yesterday's test?
Yesterday's paper I have not checked. I'll send you the marks whenever the papers get checked.
Yes, ma'am.
Okay. See, you have two bar magnets which are kept perpendicular to each other. This is first bar magnet. This is second bar magnet. Now, if this is north, this is south, this is north, this will be south. What did we study? Magnetic field we are trying to find out. So the first magnet is this. So magnetic field will be at this point due to this bar magnet and at this point due to this bar magnet. Let's talk about the first bar magnet. If this is the magnetic axis, all these terms we have already studied: magnetic axis, magnetic equator. Now see, this is the axis of magnet. Can anyone tell, is this point P axial to this bar magnet or equatorial? Axial or equatorial?
Ma'am, axial.
See, how do we see axial and equatorial? If the point lies on the, yes, it is equatorial. Because if the point lies on its axis, this is the magnetic axis, if the point lies on this line, then we say it is axial. If this point lies perpendicular to this magnetic axis, we say it is equatorial. So this point is lying on the perpendicular side of this axis. Now see, for the second, see, now this is point is lying on the magnetic axis of the second one. So for the first one, it is equatorial. Second one, it is axial. Net magnetic field will be given by B1 plus B2. Now B1, that is magnetic field due to the first bar magnet. First bar magnet, when we'll consider it? For equatorial. So for equatorial, yesterday we had seen the formula was 2, then K was there, mu naught by 4 pi M by R cube. Let's say the separation is smaller, as well as this separation, and this separation is smaller between both the magnets. Plus, then you have for axial line minus K M by R cube. So this is, so I think let's not write this plus sign. Directly we can put this negative sign. This is your net magnetic field. Magnetic field's magnitude. This is just the magnitude that I've written. Now you have to add on the direction as well. See, if this is a bar magnet, north to south, magnetic fields will run from north to south. For equatorial line, you put the direction as opposite. This is done in electrostatics only. So that's why I'm saying just refer to the playlist once. I have sent it on the group as well. Just refer to it once. See, direction of magnetic field is north to south. Whatever is the direction of magnetic field, we put it opposite for equatorial, and same for axial. Here it is north to south, so this will also be north to south. So this becomes your J cap, this becomes your minus I cap. J cap for here and minus I cap for here, like this. Got it? Whatever is your unit vector, just put your unit vector. Accordingly, whatever will be the question, you can answer it. Fine, note this down. Done?
Yes, ma'am.
This is one more important question that we have to cover, that the motion of a bar magnet in uniform magnetic field is in SHM. So what is meant by SHM? SHM is simple harmonic motion. Now, what is meant by SHM and waves? You already have it in your class 11. So you people must have done it before entering class 12. So let's just quickly revise. For any motion to be considered under SHM, whatever is the force applied has to be proportional to the displacement, and we write it as F is equal to minus K of X. This equation you all must have done it. Now, F is the force, X is the displacement, and K is the constant. The spring factor we call it mainly. So for different systems, this value of K differs. Like if you have spring mass system, then the value of K is different. Spring pendulum bob system, it is different. So different systems, you have the value of constant different. If it is rotational, this is for linear. This is for linear. If it is rotational, then your torque is directly proportional to angular displacement. All the analogs come into action. Force becomes torque, linear displacement becomes angular displacement. So torque becomes minus K theta. This is for rotational. So linear SHM's condition is this, and rotational SHM's condition is this. Now this negative sign simply say that the restoring force tends to act towards the mean position. There is a certain equilibrium position of the body, and when the body starts its motion, the simple harmonic motion, the restoring force tends to put the body back at its original position. That's why we have this negative sign, and magnitude of force is directly proportional to displacement. Similarly, magnitude of torque is directly proportional to angular displacement, and minus sign again shows that restoring torque is acting towards the mean position. That's why we have these formula. Now what happens now is given a case to all of you that magnetic field lines exist. A bar magnet is kept. Now torque will come into action. Somehow torque's work will be to rotate the bar magnet and align it in the direction of magnetic field. Somehow to rotate it in such a direction that it gets aligned in the direction of magnetic field. Now, we have already studied the formula for torque. Yesterday, torque was what? M cross B. Formula of deflecting torque was what? M cross B. This was magnetic dipole moment and this was magnetic field. I can write this as MB sine theta as well. Fine. Now see, for small angle approximations, you have to understand this small angle approximation. See, if your angle is less than or equal to 15 degrees, you say your angle is a small angle. Fine, 10 degrees, 9 degrees, 3 degrees, like this. Less than or maximum it is equal to 15 degrees. You say your angle is very less, small angle approximation. Fine, theta is less than or equal to 15 degrees. Now, if you have small angle approximation, your tan theta and sine theta, both of these, tan theta as well as sine theta, either of these or both of these, both of them become equal to theta. So whole sine component gets equal to theta. Now, for small angle approximation, theta is less than or equal to 15 degrees. Tan theta or sin theta is equal to 0 degrees. Now, I can write torque was equal to mb sin theta. So instead of this sin theta, I can write it as theta only. Why? Because see, if a bar magnet is rotating, it will not rotate so much. No? Even if a magnetic field is there and a bar magnet is kept, because of the external magnetizing field, a slight deflection will be observed in the bar magnet. Got it? A very small deflection will be observed. Unless and until an external force is applied, an external torque is applied, that is separate. But if it is within the system, in the presence of magnetic field, slight deflection will occur in the bar magnet. So that's why here we can use small angle approximation. Your torque will become equal to mb theta. Fine. Now the restoring torque will always act towards the mean position. So we have actually got our equation. Just talking about the magnitude. Tau is equal to k theta. Tau is equal to mb theta. It means from here, if you look carefully, mb is this is the constant k spring factor that you are obtaining. So you can directly say this shows that bar magnet executes SSM, and the constant you're getting, spring factor you're getting as MB. M is what? Your magnetic dipole moment, B is your magnetic field. Now you can even, if you remember, you must have done angular velocity is equal to K divided by I. Fine, K divided by I. So here also for the value of K, you can put as mb divided by I. If angular velocity is asked, till here this was enough to prove your answer. Till here you can leave your answer at this stage. But if it is asked, angular velocity is also asked, you can put it like this. Then using this, you can calculate linear frequency. Using this, you can calculate time period and rest of the things which are related to angular velocity. And you have already done that. Fine. So your question's answer was completed till here. This is just an extension. What can be asked to you in the examination? So this is not a numerical. It's a proving question that you have to prove that the bar magnet executes SSM. Got it, class? So just note it down. Note down this question and try this once. See, it says what a magnetized needle of magnetic moment, which is 4.8 into 10 to the power minus 2 joules per Tesla. This is what? This is the magnetic moment. It is placed at 30° with the direction of uniform magnetic field. Fine, magnetic needle is placed at 30° with the field, and magnitude of magnetic field is 3 into 10 to the power minus 2. Torque you have to calculate. Magnetic moment is given, magnetic field is given, angle is also there. You have to find out torque. Take 2 to 3 minutes, try this question, then we'll discuss it. Yes, Asta, right. So, Asta, what's the angle that you have written?
Sine 30°.
And magnetic field, this?
I'm asking the formula, the angle.
No, I'm asking you the terms that you have written. So, magnetic moment you've written as 4.8 into 10 to the power minus 2, right?
Yes,
And
ma'am.
magnetic field as 3 into 10 to the power
3 into
minus 2.
10 raised to minus 2. Yes.
Razan has also answered it correctly. The magnetic moment to you is given as 4.8 into 10 to the power minus 2. And magnetic field, this is given as 3 into 10 to the power minus 2. Theta is also given to you as 30-degree. Torque is asked. Torque is m cross p, which you can write mv sine theta. So torque will be 4.8 into 10 to the power minus 2 into 3 into 10 to the power minus 2 into sine 30-degree. That is half you will write. So this becomes what? 2.4, 2.4 into 3. This will give you 7.2 into 10 to the power minus 2. You can write Newton meter for the unit, or you can put the units of dipole moment and magnetic. It's better if you write Newton meter. This will also go. And a very small question was there. 2 students were able to answer it correctly. Note this down.
Ma'am, the tens power is -4, right?
Yes, 10 to the power minus. See, some terms are left that are used to describe the magnetic field and magnetism. So very few terms are left. We'll do these one by one, but these are important. See, these definitions can be asked. The other terms that we did know in the first class of magnetism and matter, that included magnetizing, all those terms that we have done, magnetic properties, attractive property, directive property, that will not be asked in the exam directly to define it. It can be clubbed together and asked, that too in very rare cases. This can be asked from here. That's why I've written this separately, because this gets connected to your differences between diamagnetic, paramagnetic, ferromagnetic substances. And that you have to remember on your own. I'll resend you the table if you wish. On the group, I'll resend you the table, but you have to remember and learn that table well. Otherwise, answering the questions of this will become difficult for you all. Questions mainly come from that part. Theoretical questions can be asked like, what are the properties of diamagnetic substances? Or what is the magnetization intensified by the diamagnetic substance in presence of external magnetic field? So you don't have to apply brain in these questions. You just have to remember, will it increase, decrease? Will it show feeble attraction, feeble repulsion, like this? I'll give you brief discussion, we'll do it, but remembering part and learning part you have to do on your own. Otherwise, you'll not be able to remember that. Fine? Yes, so let's start with this. First term is magnetizing field. Now see, when a magnetic material is placed in a magnetic field, a magnetic material is there and this is placed in a magnetic field. So magnetism is induced in it. For example, we had done that example of iron ball as well. If iron ball is present and bar magnet is continuously rubbed on the iron ball, so a time will come that iron ball will itself induce magnetism for a temporary moment. Similarly, when a magnetic material is placed in a magnetic field, magnetism is induced in it. So you say magnetic field. Basically, to understand a magnetizing field in simple words, you can remember magnetic field in vacuum and induces magnetism. Just remember this. And induces magnetism. And yes, class, now the upcoming terms will be very confusing for you all. Magnetizing field intensity, intensity of magnetization, all will be different. With the name, it will be a misnomer for you all as well. Some terms will be confusing. So just pay a little attention over here. So whenever a magnetic material is placed in a magnetic field, magnetism is induced in it. And the magnetic field that exists in vacuum and induces the magnetism, this is known as a magnetizing field. For example, you can consider toroid and solenoid. We have done, no? Formula of toroid and solenoid was what? B is equal to mu naught Ni. B is equal to mu naught N. So if you consider a toroidal solenoid or a solenoid simply, which is carrying current I, and this is placed in vacuum, so you won't say that this is the magnetic field. If this solenoid is kept in vacuum, then you will say this is the magnetizing field. Instead of the term magnetic field, you can use magnetizing. So this field, this is caused by magnetizing field, you can say. Simply, this becomes your magnetizing field. Rest of the properties, rest of the phenomena, SI unit as Tesla, other formulas, everything is the same. Just remember this. By this, you can easily remember. Then second term is magnetic induction. See, suppose a solenoid is there. This is a iron core is there, and on this iron core, wire has been wound up. Like this. On this you can say soft iron core, copper windings have been done, aluminium windings have been done, or you can simply say atomic current loops, these are done. So what happens is this, slowly and slowly, this was not producing any current. Fine. Now what will happen? Now you have made the soft iron core in the form of a solenoid. So what will happen? There will be certain magnetic field lines that will be present. So these magnetic field lines that are crossing this cross-sectional area of this iron core, that you will say that is magnetic induction. Fine. This is similar to, you can remember, magnetic flux. This is similar to magnetic flux. So magnetic flux, this is magnetic induction is not total number of magnetic field lines of force crossing per unit area normally is called magnetic induction. Whatever you have studied for magnetic flux, no, that is exactly same for magnetic induction. Terms are just different. And one more thing, SI unit of, you say, this is also Weber per meter square. The way what it is for magnetic, Weber per meter square, because it is like magnetic flux per unit area. Magnetic flux is there, the number of magnetic field that is crossing a surface area or area of cross section normally. Similar is the case of magnetic induction. Total number of magnetic field lines of force crossing per unit area normally. This is known as magnetic induction. So SI unit of this will be same as that of magnetic flux. Everything that you've studied for magnetic flux, it is exactly the same. Third property you have, that is magnetic field intensity, and fourth property that you have is intensity of magnetization. Magnetic field intensity and intensity of magnetization, both are different properties. We'll deal with each of it. See, magnetic field intensity means what? Magnetic field intensity means what? Magnetic field intensity is the ability of a material to magnetize, ability to magnetize a material. You can say a material medium, and this is represented by the symbol capital H. Now, what's the difference between? You can simply say it is the number of ampere turns. Ni you have no. So you can simply say this is the number of ampere turns. Number of ampere turns that is flowing around the unit length of solenoid. Flowing around the unit length of solenoid. Unit length of solenoid. Fine, ampere turns flowing. Ampere turns means what? Current that is flowing for every turn that is present. So this is equal to, simply your H is equal to N into I. Ampere turns, simply ampere turns, number of amperial turns that you have. Now B is equal to mu naught I. Mu naught Ni. And Ni is what? Ni is H. So from here you can say B is equal to mu naught H, because Ni can be written as H. And mu naught will be written as B divided by H. Or you can write the formula of H from this. From here, the formula of H will be what? H will be B divided by mu naught. Just remember, it is Ni, or the ratio of magnetic field to permeability. This is magnetic field and this is permeability. So magnetic field intensity is this. But what is meant by intensity of magnetization? So see, when a magnetic material is placed in magnetic field, it will get magnetized. This we have been studying. Now the magnetic moment per unit volume is known as intensity of magnetization. Magnetic moment per unit volume is simply intensity of magnetization. So capital M, you can denote it, magnetic moment by volume. Magnetic moment per unit volume. Fine. So this is what? This is your magnetic moment. And this is volume. It is like magnetic density whenever anything gets divided by volume. So that's why I was saying these names are confusing. Intensity of magnetization says something else, but in actuality, this is the magnetic moment per unit volume of a material when it is placed in a magnetizing field. That you call it as intensity of magnetization, or this is also simply known as magnetization. Simply, this is known as magnetization as well. But by the name, it seems that this is the intensity or the strength. So you can also define it as pole strength, but that is developed per unit area or the cross-sectional area of a material. This also you can do. Now see, one more point that is important in intensity of magnetization is, see, the total magnetic intensity that is coming or pole strength that is there. You can even relate it with pole strength. You can relate this with pole strength as well. Strength of pole. Now the net magnetic field is equal to magnetic field, that is intensity of that is normal magnetic field that you have. This is the normal magnetic field that we use in our calculations, plus it is the resultant of magnetizing field. The magnetizing field we have just done just now. So what is the full form? See, B M, you can B naught, you can write it as mu naught M, and BM you can write it as mu naught M. From here, mu naught can be taken common, M plus H can also be written. So numericals on this is not asked. If you are mentioning this point, you can mention this as well to add in your questions. This is your resultant magnetic field. One is which we have studied mu naught H right now, and other one that we have been studying mu naught M multiplied by magnetic moment. Fine. This is one thing. Do one thing. 4 points are left. So note down these first 4 points. Wherever you have confusion, ask me. Then we'll do the other 4 points. Because confusing part is in this only, especially the third and the fourth. Start noting from here. Let me know.
Ma'am,
Yes. Who is asked?
Asta. Ma'am, have to draw the diagrams also, or like, or only the definition part?
No. In the exam, only the definition part. But right now, whatever I've written, copy it down. But in the examination, no need to draw the diagrams.
Okay, ma'am.
Ma'am, can you just scroll up on just carry on.
Ma'am?
Yes, Asta.
Both capital M and small m denote the magnetic moment.
No. See, actually, you can use one thing. If you are representing capital M as magnetic moment, so just represent it intensity of magnetization as small m. There is no fixed representation. As I had written capital M initially, so that's why I had to write small m. Yeah, how are we depicting? We are, I think, using capital M no for magnetic moment till the past classes. So
Yes,
just
ma'am.
interchange, because this is not a definite symbol. Definite symbol is H. That's why I had written that symbol separately. H for magnetization intensity. Fine. So this is not a definite symbol. You can interchange as per your convenience. See, the fifth term that you have is magnet. Now the terms are not so difficult. These initial four terms were difficult, especially intensity of magnetization and magnetization intensity. Both depicted the same thing by the name, but had the meanings differently. Now, magnetic permeability is the same that we have been studying. That we denoted by mu symbol, and for air and vacuum we put mu naught, whose value we write it as 4 pi into 10 to the power minus 7. Exactly, this is what is magnetic permeability. But here we have to define it. See, permeability is a measure of the extent to which a material can be penetrated, a magnetic field can go into the material. That is known as permeability. How much a material can hold the magnetic lines, magnetic field lines, or how much into the depth a magnetic field line can go into the material. That is known as permeability. If permeability is high, number of magnetic field lines will go high. If magnetic permeability is less, the number of magnetic field lines will not be able to penetrate much into the material. But here in this lesson, that's what we have already discussed. Now, new thing here in this lesson, you define permeability as the ratio of magnetic induction and magnetic intensity. Ratio of magnetic induction and magnetic intensity. Then you have relative permeability. See, relative permeability is in terms of two different mediums. If you have two media are there, one be air, other medium be something else. Water you can take, glass you can take, a different material you can take. So relative permeability is simply the ratio of permeability in that medium by the permeability in air. This is known as relative permeability. This also we have discussed when we were discussing magnetics. That also we have discussed. So this is known as permeability. This is known as permeability. In a medium. And this is known as permeability. Permeability in air. So if you are comparing a medium's permeability with respect to air, your medium is air, then you say you are taking out the relative permeability. This is known as absolute permeability. Only mu when we write, that is meant by, that means your absolute permeability. You are not comparing, you're just writing the permeability of a medium. Whenever you compare that medium with respect to air or any other medium, you say that is the relative permeability. Fine, these two terms are easier, magnetic permeability and relative permeability. Now a term is there, susceptibility. Susceptibility is also, magnetic susceptibility measures the ability of a substance to take up magnetization. If I say a wood is there and an iron ball is there, so magnetic susceptibility of iron is higher. That's why the iron ball gets magnetized when the bar magnet is rubbed on it. But since the magnetic susceptibility of the wood material or wood is low, that's why however number of times you strike the bar magnet on the piece of wood, the wood will never develop magnetization. So that ability to take up magnetization, that is known and given by susceptibility. We denote this by this symbol, chi. X we write no, so an extended form of it. X. This we wrote, this we called as, the symbol is known as chi. So using this symbol we denote the magnetic susceptibility. So it's the ratio of what? It's the ratio of intensity of magnetization and the magnetic field intensity, both of these terms. This is what M is your intensity of magnetization. Intensity of magnetization, and this is what? This is your magnetizing field intensity. Magnetizing field intensity. Fine. So since it's the ratio of the two quantities that have the same units, because intensity of magnetization also is ampere per meter, this is also ampere per meter. So see, regarding the SI units. Units, one is ampere per meter square. This is also ampere per meter square. So you get no unit. So this is a chi, magnetic susceptibility is a unitless quantity. And one more last term is there, that is not a term. Basically we have a relation between the magnetic permeability we did just now, remember, magnetic permeability, and this term magnetic susceptibility, and that can be asked to you separately in the exam. So that is important, this relation between mu naught and chi m. Class, this is important. Do mark it in your notes whenever you're writing as important. This has separately been asked. Rest of the properties, these are not so asked separately, but this has been asked in your exams. Now, this relation we have already discussed, H plus M. Now, B is equal to mu H. B is your magnetic field, normal in terms of your permeability, not exactly permeability of air. You can write it as mu H from B is equal to mu Ni. Mu naught is different, mu is different. That's why we have studied magnetic permeability. This is magnetic permeability. This is magnetic permeability, especially for air in vacuum. So this is one relation. Put it, mu H is equal to mu naught H plus M. Now see, let's do one thing. Let's divide it by H. Divide by H. So here H gets cancelled, mu is left. Mu naught H by H will give you 1 plus M divided by H will be left. M divided by H. We have just done one thing. Can you remember it? I'm not scrolling up. Can you remember it? M by H. Just now we did it. What was that quantity that we have just completed? Susceptibility, magnetic susceptibility. M by H, no, this is magnetic susceptibility. So from here you can have magnetic susceptibility. So this is the relation mu naught 1 plus chi. Mu is equal to mu naught 1 plus chi m. Fine. This relation is asked in the exam. Numericals are rarely asked from this lesson. From this part especially. Otherwise, numericals from that equatorial line, axial line, those numericals that we have done in the beginning of the class is already asked. But this relation part is asked, numerical on this is less. So from here, note it down. Whatever doubts you have asked me, I'll clarify. 4 points you've done, 5th you have to write it, no? Right. Written till here. Mu is equal to mu naught 1 plus chi m. See, this part you don't have to note it down because as I've told you, I'll send you the table. Just for discussion, I've written it. This is important. This is very important, but you have to remember. For diamagnetic substances, they exhibit feeble magnetization. It means weak magnetization. And the magnetization occurs in opposite direction to that of magnetic field. And it is weakly repelled by magnets. So see, all these points I'm just explaining once, but you have to remember the points on your own, because these points are very theoretical points and you have to learn these. So they are feebly repelled by the magnets, and the magnetic field it goes into opposite direction to that of magnetic field. Now, the magnetic field lines tend to move from the stronger to weaker parts of magnetic field. All these are valid for a diamagnetic substance, be it copper, lead, silver, gold. So, feeble magnetization in opposite direction to magnetic field, feebly repelled. Feeble means weak, weakly repelled by magnetic field. Then you have paramagnetic substances. It also exhibits feeble magnetization, but in the same direction of that of magnetic field. Weakly magnetization in the same direction of magnetic field. They are weakly attracted by the magnets, and see, they were weakly repelled by the magnets, diamagnetic. Here, the paramagnetic are feebly attracted by magnets. That's the difference that comes. And the magnetic field lines tend to move from weaker to stronger paths. Weaker to stronger paths means from where the magnetic intensity is lower to the stronger paths. These comprises your ionic substances like NaCl, copper chloride, aluminium, manganese, chromium. 1 or 2 examples you can remember. Not more than that, because examples separately will not be asked to you. You just have to mention it at the end of your answer. Last group of substances include your ferromagnetic substances. So they have strong magnetization. Other two had weaker magnetization. These have strong magnetization. And in the same direction, diamagnetic was feebly repelled, paramagnetic was feebly attracted. Here, ferromagnetic have strongly attraction by the magnets, and same tend to move from weaker to stronger parts. So iron, cobalt, nickel, all the alloys that you have. One alloy is alnico, that is made up of aluminium, nickel, and cobalt. So these chemistry part will be asked to you in chemistry. In physics, remembering 1 or 2 examples is important to enhance your answers, because if the difference comes in writing these many points are enough. No need to copy it down in your notes, because as I've told you, from that table, which I'll send you can remember, or directly from the NCRT you can do. Fine, from the NCRT also you can do, and from the table that I'll send you. So if on the group you're not able to find it, let me know. I'll